Why does a boiled potato taste saltier than a fried one, even when both have the exact same amount of salt? That's the curious potato paradox, a sensory illusion rooted in chemistry, physics, and human perception. At first glance, it seems impossible. Salt is salt, right? But when it comes to taste, how salt is delivered to your tongue matters as much as how much is there. Boiled potatoes absorb water and salt uniformly during cooking, allowing salt ions to penetrate deep into the soft, hydrated interior, making every bite taste consistently seasoned. In contrast, fried potatoes, like crispy fries or chips, have a dry, oily exterior that repels water-based salt solutions. Most of the salt stays on the surface and doesn't dissolve easily, meaning it doesn't always reach the taste receptors as effectively. Additionally, the crunch and fat content of fried potatoes can dull the perception of saltiness, while the softness and moisture of boiled potatoes enhance it. So despite having identical salt content by weight, your brain and taste buds experience them very differently. The potato paradox reveals a fundamental truth about flavor. Taste isn't just chemical, it's physical, biological, and deeply contextual. Potato paradox. Why do boiled potatoes taste saltier than fried ones at the same salt level? How can two potato preparations, each seasoned with identical amounts of salt, yield one that tastes boldly savory and another that seems comparatively bland? Boiled potatoes soaked in salted water often deliver a punch of saltiness that fried potatoes, sprinkled with the same salt after cooking, somehow miss, creating a sensory puzzle far deeper than the shaker count. What really makes the difference? When you boil potatoes, salt dissolves in the cooking water and seeps uniformly into every cell. Each bite carries dissolved sodium ions straight to your taste buds. In frying, by contrast, oil replaces much of the water, and salt sits largely on the crust's surface. The interior remains low in dissolved salt, so most bites deliver fewer ions to your tongue, even if the total grams of salt are the same. At its core, this paradox hinges on salt distribution versus total salt. Boiling integrates salt into the potato's flesh, creating a consistent, high local concentration. Frying applies salt externally, where it clings unevenly to crisp edges and often fails to penetrate the starchy center. Your palate responds to that local concentration, not the global tally. Could texture and temperature play tricks on us? Absolutely. Hot, moist surfaces dissolve salt instantly on contact, flooding taste receptors. Crispy fries, however, may trap salt crystals in oil films or pockets of dry starch, delaying dissolution and muting that initial hit. Cooler interiors of fried potatoes also reduce salt's solubility and the speed at which sodium ions reach your tongue. Does flavor chemistry add another layer? Yes, frying triggers the Maillard reaction, browning that creates rich, complex aromas and flavors. These new notes compete with salt, diverting your attention and masking some of its sharpness. Boiled potatoes lack these competing compounds, so salt stands front and center. What's the take-home lesson? Saltiness is all about where and how salt meets your taste buds. A boiled potato saturated with saline water serves each bite with a direct hit of dissolved ions. A fried potato, crisped and oiled, delivers salt more sparingly and amid competing flavors. If you want fries as savory inside as a boiled spud, you'd need to infuse them, perhaps by steaming with a fine mist of saline, so salt migrates inward rather than just dusting the surface. The potato paradox shows that cooking methods sculpt not just texture and aroma, but the very perception of seasoning. Even when the salt shaker is unchanged, the journey from potato to palate can transform same salt into two very different taste experiences. The potato paradox reveals that identical quantities of salt do not always produce identical perceived saltiness, especially when comparing boiling and frying. When equal amounts of salt are applied to potatoes, those boiled in salted water taste noticeably saltier than those fried with the same salt level. This arises because during boiling, salt dissolves uniformly throughout the potato's intercellular spaces, whereas frying deposits salt mainly on the surface. The result is a more pronounced saline taste from within the flesh rather than just a surface seasoning. This challenges the intuition that identical salt quantities always yield identical saltness. A peeled potato cube boiled in 1 teaspoon of salt per liter will register a stronger salty flavor throughout than a pan-fried cube tossed in an equivalent spice. It is like soaking a sponge in salted water. Every pore holds salt, versus sprinkling salt on a waterproof raincoat's exterior, where most of the material never feels the seasoning. Surface seasoning involves salt crystals adhering to the food's exterior, providing an immediate but shallow taste. Salt uptake, by contrast, integrates sodium ions deep into the food matrix, altering the overall ionic strength of the tissue. Boiling promotes uptake as salt-laden water penetrates cells, whereas oil in frying is a poor solvent for sodium chloride. Recognizing these two modes clarifies why identical quantities of salt can produce different perceived intensity. Chips dusted with fine salt remain salty only until the next bite, while boiled potato wedges retain a steady saltiness from core to skin. It is like painting only the surface of a wooden door with waterproofing versus infusing the wood with preservatives so every layer resists moisture. In aqueous environments, sodium and chloride ions diffuse rapidly, moving along concentration gradients into cell walls and vacuoles. Oil, being nonpolar, cannot dissolve these ions, so salt remains largely immobile during frying. Consequently, boiled potatoes achieve deeper ion penetration before cooking ends, while fried potatoes only season their crispy exteriors. The microscopic difference in solvent compatibility underpins the macroscopic taste contrast. In a sensory test, points measured along the radius of a boiled potato show uniform salt levels, whereas fried samples drop to near zero, just a few millimeters below the surface. It is like dyeing a cloth by soaking it in water-based dye versus brushing on oil-based paint. Soaking colors every thread, brushing paints only the surface fibers. During boiling, cell membranes become more permeable from heat, opening channels that facilitate salt ingress into intracellular spaces. Diffusion continues until the salt concentration inside the potato equilibrates with the cooking water, creating a gradient that enriches deeper tissue. In frying, surface moisture evaporates quickly, forming a crust that impedes further penetration of any added salt. These distinct diffusion pathways explain why boiling yields uniform salinity while frying does not. Microscopic cross-sections of boiled potatoes reveal salt crystals dissolved between starch granules, whereas fried specimens show crystals perched atop collapsed cell walls. It is like watering a plant so the soil absorbs moisture thoroughly versus misting its leaves, which wets only the outer layer before evaporating. Water acts both as a heat transfer medium and as a carrier for salt ions, ensuring even heat and seasoning distribution. Oil transfers heat efficiently but lacks the chemical compatibility to carry salt beyond surface contact. Moreover, high frying temperatures dehydrate the potato surface, forming a moisture barrier that further limits salt ingress. Understanding how water and oil interact with food surfaces is key to mastering seasoning techniques. Sous vide cooking in a salt brine at low temperature also yields pronounced internal seasoning, echoing the principle of aqueous transport. It is like using a saline bath to infuse fish with flavor throughout versus brushing on a salty glaze and grilling, which flavors only the crust. Salt perception is temperature dependent. Warmer foods often taste less salty because heat stimulates other taste modalities and reduces sodium chloride's perceived intensity. Boiled potatoes served piping hot may register higher saltiness after cooling into their optimal tasting range. Fried potatoes served hotter and crisp can paradoxically taste milder despite higher surface salt due to thermal masking and rapid mastication. These nonlinear sensory effects compound the physicochemical differences. A boiled potato at 60 degrees Celsius tastes saltier than the same sample at 80 degrees, as measured in blind taste panels. It is like adding sugar to a hot cup of coffee. The sweetness is muted when the drink is scalding, compared to when it's warm enough to sip comfortably. Chefs leveraging this paradox can achieve consistent internal seasoning by salting cooking water or brining ingredients before final high-heat treatments. Conversely, surface seasoning should be adjusted upward for fried or baked preparations to compensate for shallow salt penetration. Balancing salt levels in multi-step recipes such as boiling, then sautéing, requires understanding where and how salt moves. Mastery of these principles leads to better tasting, more uniformly seasoned dishes. Professional kitchens often brine potatoes overnight before roasting, ensuring deep seasoning while still achieving a crisp exterior. It is like priming a wall with a deep penetrating sealant before painting, so the finish coat adheres evenly and looks consistent. Human salt perception varies with individual sensitivity, mouthfeel, and the presence of other flavors like umami or fat. Reproducing precise salt levels demands standardized protocols for cooking times, salt concentrations, and serving temperatures. Small deviations in potato variety, water hardness, or oil quality can skew results. Rigorous sensory testing and instrumented salinity measurements are necessary to quantify and control the potato paradox reliably. Two kitchens using the same brine recipe often report different seasoning outcomes due to slight differences in tap water mineral content. It is like calibrating a piano by ear in two different concert halls. The same chord can sound crisp in one room and muddy in another. Emerging techniques such as real-time salinity sensors, 3D food printing with embedded brine channels, and molecular gastronomy methodologies promise finer control over internal seasoning. Quantitative food science models integrating diffusion kinetics, thermal profiles, and sensory response curves can predict optimal salt strategies. Beyond potatoes, these insights apply to brining meats, vegetable pickling, and developing low-sodium products with full flavor. Ultimately, understanding why boiled potatoes taste saltier than fried ones deepens our mastery of taste, texture, and culinary innovation. Pilot studies using ion-selective electrodes embedded in potato tissue map real-time salt diffusion during cooking, guiding dynamic seasoning adjustments. It is like having a smart irrigation system that monitors soil moisture and nutrients continuously, delivering precisely the right feed at the right depth for optimal plant growth.